Why was the universe born with a kind of reservoir? Think of it as a wellspring of order, one that slowly unravels over billions of years, giving rise to complexity galaxies, stars, life. In January 2025, a remarkable experiment brought us closer to understanding this cosmic order. Google's Quantum AI Lab, working in collaboration with NASA and Caltech, launched a pioneering study. They processed raw, unfiltered deep-field data from the James Webb Space Telescope using one of the world's most powerful quantum systems. What they uncovered was staggering, unusual patterns in light, energy variations, and signatures that defied current cosmological models. Almost immediately, the quantum algorithms began identifying strange relationships in the data that pushed the boundaries of our knowledge about gravity, dark matter, and cosmic dust. These weren't vague statistical flukes. The patterns were clear, structured, and persistent. The results hinted at physics beyond our current understanding. Could this be a new natural phenomenon, the dawn of a computational age, or something even deeper, a revelation about the nature of the universe itself? In early 2025, Google's Quantum AI division teamed up with astrophysicists from Caltech's IPAC Research Center. Their mission: tackle a problem that had long stumped even the most powerful classical supercomputers, modeling the quantum state of cosmic light. They directed their quantum processor untouched datasets, raw photon counts, spectral curves, and gravitational lensing maps collected from the deepest field exposures by the James Webb Telescope. These datasets had been waiting dormant for the right kind of tool. Within mere hours, the quantum processor began surfacing unexpected signals. First, there were curious variations in energy bands, especially in the infrared spectrum. These shifts suggested processes unknown to modern astrophysics. Then, the system detected correlations between photons originating from widely separated galaxy clusters. These subtle interactions spanned immense distances, implying some form of coherent structure across space. Repeated analyses, seeded with fresh randomness, returned the same results again and again. Fluctuations in light were aligning across multiple observations. The most breathtaking discovery came when these fluctuations were mapped to spatial coordinates. They formed faint arcs, geometric patterns that weren't just random noise. These arcs appeared repeatedly in different fields of view. It was unmistakably a signal, not statistical static. Something within spacetime itself seemed to be expressing an underlying order. And if this excites your imagination, stay tuned. This breakthrough touches not just science, but the very foundations of reality. To understand the magnitude of this, we need to rewind. Classical supercomputers are incredibly capable, but they're constrained when modeling quantum-scale events. They reduce quantum behaviors into averages, smoothing over the very effects that might reveal new physics. Quantum computers, on the other hand, manipulate information in qubits units that exist in multiple states simultaneously. This allows them to naturally model quantum entanglement and multi-particle interactions. That makes them ideal for studying enormous quantum systems, such as interstellar photon clouds shaped by quantum gravitational corrections. When the James Webb Space Telescope launched in 2021, it promised to reveal the earliest galaxies in the universe. It delivered, showcasing stunning visuals of stellar nurseries and ancient galactic collisions. But all of those images had been filtered, processed, and interpreted through algorithms designed for classical computers. Google's team posed a bold question: what would happen if they bypassed those classical filters and fed Webb's raw data directly into a quantum processor? What secrets might lie hidden beneath our assumptions? The answer was profound. The unprocessed light data revealed interactions that current models can't explain. These weren't faint or ambiguous. They spanned across tens of arc minutes and intersected with known dark matter structures. By early morning, the global scientific community was abuzz. Could we be witnessing the early indicators of quantum effects woven into the fabric of the cosmos? This brings us into the realm of early universe cosmology. Modern theory tells us the universe began as a hot, dense state. Over time, structures such as galaxies emerged, and their energetic processes helped reionize the cosmos, making it transparent to light. During this reionization period, certain conditions, like bursts of intense star formation, might have preserved quantum information within photons. The quantum AI picked up phase correlations in those photons, matching predictions related to those early stars. The patterns weren't limited to a single wavelength, they appeared across near and mid-infrared bands. This ruled out interference from cosmic dust or instrumentation. What emerged were coherent signals aligned with reionization models. So what if Webb, through raw light data, has captured echoes from the cosmic dawn? What if these photons carry a quantum imprint from the universe's infancy? Each arc of light might not just be a distant galaxy, it could be a historical trace, a message in light from the universe's beginning. Just as the excitement peaked, the researchers made a second discovery, a gravitational anomaly. When they overlaid photon maps with known dark matter structures, something unexpected emerged. On one side of a field, galaxy clusters bent light as predicted. But across the field, some clusters showed slight deviations suggesting gravitational influence from an unseen mass. The anomaly appeared in 3 separate regions of the sky, implying a deeper phenomenon. One researcher described it as seeing ripples in a pond, ripples caused by an invisible object. This subtle disturbance suggested that dark matter structures might be more dynamic, complex, or varied than we ever assumed. By mid-morning, the team realized they weren't merely mapping curiosities, they were exploring brand new aspects of spacetime itself. If these patterns reflect undiscovered gravitational effects, what does that mean for our understanding of physics? Are there unknown structures guiding the evolution of the cosmos? If you followed this far, you're among the few willing to entertain these deeper questions about the nature of space, time, and consciousness itself. Now let's go further into the intersection of physics and philosophy. Decades ago, physicist John Wheeler proposed the participatory universe, the idea that reality isn't a fixed object awaiting measurement. Instead, the act of observation helps bring the universe into existence. According to Wheeler, the cosmos participates in its own unfolding. Reality takes form when it is observed. That theory may once have seemed speculative, but quantum AI gives it renewed relevance. When a quantum computer processes entangled photon data, it isn't just calculating, it's engaging with raw quantum information, interacting with wave functions that haven't collapsed. In essence, it becomes an observer, and when it did, something unexpected happened. Rather than producing standard output or random noise, the processor revealed structured data patterns that hinted at deeper, hidden orders. This opens the door to even more provocative ideas like the many worlds interpretation of quantum mechanics. According to this theory, every quantum event creates a branching universe. Each decision, each photon's path, spawns a new branch of reality. Usually, these parallel worlds remain isolated, unaware of one another. But what if that boundary isn't impermeable? What if an advanced quantum system could detect echoes or entanglements from these alternate branches? What Google's AI uncovered may not just be cosmic patterns, it could be subtle evidence of entangled realities. Not just data structures, but echoes of parallel events. When millions of quantum measurements are made on entangled cosmic data, could they temporarily align to reveal hidden structure? One physicist summarized it chillingly. We're not just looking at the universe may be revealing itself to us. At this point, the borders between science, philosophy, and metaphysics start to blur. Quantum computation becomes more than a method, it becomes a key to unlock hidden dimensions of reality. For centuries, we've studied the cosmos from the outside, but what if we're not outside observers? What if, in measuring, we are participating in the creation of reality itself? And just when this journey seemed as surreal as it could get, another discovery shook the room. During a quiet late-night session, a sub-team chose to analyze something most researchers ignored, the spectral noise usually dismissed as background error. They ran it through a signal analysis model, expecting randomness, But what emerged was anything but random. The noise showed structured patterns, resembling mathematical sequences, prime number-like formations emerging across various sky regions, wavelengths, and times. The probability of this occurring by chance? Incredibly small, but not impossible. Two explanations emerged. One, an unknown astrophysical process might, under rare conditions, create structured light. Perhaps something about early star formation or gravitational lensing. The second possibility was more speculative. Maybe this was a relic of early universe physics, a natural imprint from the reionization era. These mathematical patterns could have arisen naturally, not through intelligence, but through the very laws of physics.